Premature bearing failures. 4 reasons for preventing premature failure. First one, 36% of all bearings that we see in the market today that have failed due to lubrication issues. This might mean too much lubricant. It may have meant not enough lubricant. It could mean mixing lubricants that sometimes are not compatible, but the bearing has failed due to lubrication issues. 14% of all bearings have failed due to seal failure and contamination issues. And a further 16% have failed due to incorrect mounting procedures. And then finally, the remainder have failed due to old age. So this gives us a picture of why bearings have failed. And obviously, if we're in the design business, we can do something about the 34%. We can change designs, we can improve things. If we're in the maintenance business, obviously the other 2/3 we can do as well. So that gives us an overall picture of why bearings fail. Now, when we come to mounting bearings, the most important thing is, before we start, is health and safety, risk assessments, permits to work, proper mounting procedures, so on and so forth. We should always wear the correct suitable PPE. Obviously, if we're handling hot bearings, we wear hot gloves. Obviously, toe detectors for protecting our feet. Most importantly, safety glasses for protecting our eyes, because again, obviously bearings are very hard. If we strike them with a hard object, we get splinters of material flying off that could cause us damage. So certainly eye protection is very important. And again, lifting equipment, using the correct slings, lifting tackle, are they loaded correctly, so on and so forth. So before we do any of the actual physical work, the health and safety aspect is very important. Also, again, before we start any work, preparation stage, make sure we assemble the parts in the correct order. Make sure we have the correct parts, make sure we have the correct bearings, make sure we have the correct seals, make sure we have the correct lubricant and enough of it. Make sure that we're going to fit the bearings in the correct way. We are thinking of maybe pressing the bearing on. Is this good enough? Maybe we need a bearing heater. Have we got the correct tools? Again, have we considered that when we fit the bearing? Do we need a bearing heater? Do we need hydraulic equipment? All these things we need to think about before we start the work. And obviously, studying drawings can go a long way to solving these pre-work problems. From a bearing point of view, we should always leave the bearing in its packaging before we start work. Try and unpack the bearing just before we're about to fit it. Bearings are very precise objects, and if we get muck and dirt in them, that will affect the long-term running of that bearing. So try and keep things as clean as possible, use the correct tools, and keep the bearings in the box long enough to keep them protected. Bearings, they have clearance in them, and if a bearing has no clearance, it causes problems when it's running. It will become stiffer, more difficult to rotate. If it's in a particularly hot application, it won't be able to expand due to the heat in the application. Also, again, if the bearing has no clearance in it, it won't be able to misalign or deflect. If when we fit the bearing on the shaft or on a tapered sleeve or on a tapered shaft or into a housing, If there's no clearance in the bearing, this will cause the bearing problems when it's fitted, because the bearing, when it's fitted, the clearance reduces. And then again, obviously, if the bearing has no clearance in it, it makes it difficult to build up a lubrication film between the rolling elements in the bearing itself. So the clearance in the bearing has a huge impact on the surface life of the bearing. Here we see here, this graph on the left-hand side, it shows the effect of clearance and preload. Preload is basically negative clearance. And we can see here that up the left-hand side of the table, we have service life, and the optimum service life is actually when the bearing is very, very slightly preloaded. And we can see from the three diagrams on the right of the bearing in various stages of clearance and preload, that slight preload gives us optimum life. But in practice, preload is very difficult to measure because it's no clearance at all. Clearance is easier for us to measure with a feeler gauge or with a dial indicator. So generally, we tend to head towards very slight clearance when we fit bearings. Now, bearings generally are marked with a clearance number on them, and you can have the same size, same type of bearing. It can have 6 different clearance values in it, and this will normally be marked on the face of the bearing outer ring. And if there's no markings, generally we assume that the bearing has normal clearance. And the reason why we do this is not because we like making different types of bearings. It's because of the application that the bearing is being fitted into. If we have particularly hot applications like kilns, ovens, or high-speed applications, those types of bearings tend to have bearings with higher clearance in them, C3, C4, C5. If we have situations where we may have, say, precision bearings like machine tool spindles, grinders, milling machines, they tend to have less clearance in them, because obviously what we don't want is movement of the machine spindle itself. So it's all application dependent. So we need to double check, again, it comes back to one of the previous slides. We need to make sure we have the correct bearing part number before we tackle the job. Now, as I mentioned earlier, when we mount bearings, the clearance actually reduces. So again, we need to make sure that this is taken into consideration when we select the bearing that we are about to use, because whether the bearing's being fitted to a tight shaft or a tight housing, it will reduce its clearance when it's fitted. This shows the effect of incorrect components. If we have an oversized shaft or an undersized housing, it has the effect of compressing the bearing. It reduces the clearance within the bearing, and that creates high operating temperatures. It also creates high mounting forces when the bearing is fitted, and eventually it can lead to the rings failing and the bearing collapsing. If we have fits that are too loose, what happens is that basically bearing can rotate on the shaft. Because the circumference of the shaft is slightly less than the circumference of the bore of the bearing, for every rotation you get a little bit of lag, and over a period of time, this particular application, this particular example, is a bearing running at 3,000 RPM for 10 hours a day, and you can get up to 2 kilometers of relative movement for just a very small amount of clearance between shaft and bearing bore, and in this case 13 microns. So it's important that we have the correct fits when we mount our bearings, otherwise we end up with something like this happening. This is nothing staged. This is actually true pictures of what's happened to a customer's piece of equipment. The bearing has become loose on the shaft, and basically it's worn away the shaft, and also it's worn away and swaged itself to the extent where there's massive clearance between itself and the shaft. So it's really important that we get these fits correct. The type of fit we select is very dependent upon bearing type and also load as well. Roller bearings, because they carry more load than ball bearings, tend to have heavier fits. Larger bearings tend to have heavier fits than small bearings, again, because it's coming back to how much load the bearing carries. That normally determines the amount of fit or interference that a bearing has. And here we see on the right hand side this picture here, which depicts, if we look at the green bands, bearings, when they're manufactured to a nominal size to minus. So the bore of the bearing is a nominal size or slightly less. The outer diameter of the bearing is a nominal size or slightly less. And then we have to apply that to the shaft fits and the housing fits, which again will have tolerances to them as well. So when we select the correct fit for a bearing, we have to consider all of these things to get the right outcome. And this is an ISO standard table that designers use for selecting fits for bearings on shafts and in housings. If we look at the top bands, these are capital letters followed by a number. These are housing fits. The bottom ones are lowercase letters followed by a number. These are shaft fits. And going from left to right, at the top, capital F7, that's the actual tolerance band of the housing. And we can see that the tolerance band for an F7 is always larger than the OD of the bearing. So a capital F7 housing fit is in fact always clearance. Going right the other way down to capital P7, we can see that band is always overlapping the bearing outer diameter. So a capital P7 is always an interference fit. And then in between that, we have various tolerances that go from clearance to transition to interference, regardless of whether it's shaft or housing. The general rule of thumb with bearings is that the part of the bearing that is rotating generally has the interference fit. And in most applications, the shaft is rotating. So the bearing inner ring generally has a fixed or an interference fit on the shaft. The bearing outer ring generally is stationary, and that has a clearance or free fit in its housing. Now, when we come to put things together, again, we have preparation, and sometimes we have components that are mounted to the shaft before the bearing. We have things like end covers, we have seal rings, we have spacers. So we study the drawing, we look at the components that need to go onto the bearing before the bearing itself, because what we don't want to be doing is obviously taking it all apart again. So we look at the drawing and we decide what components go on the shaft first, and most of those components will be a clearance fit. So to get them sliding on the shaft, we lubricate them with a thin oil, and the same goes for things like seals. We lubricate them with a nice thin oil. Nothing heavy like grease or paste, because this has a tendency to bung up things and stop them from moving so readily. So we use a nice light oil. We use anti-fretting pastes on things like sometimes bearing outer rings, couplings, those sorts of things. When we have oil injection channels, we need to make sure before we fit the bearing again, those ducts and grooves are all nice and clean. What we don't want is swarf and dirt and muck in those. So again, maybe using an airline or something similar, we blow those out to make sure all of those components are nice and clean as well. Where we have bearings that are moving on surfaces, i.e. a tapered sleeve or a tapered shaft, again, good practice would be to apply a light oil to the moving components to make sure they slide and don't pick up. And again, don't use heavy grease or pastes. What you want is something that slides nice and easy, but is well lubricated, and generally a good quality light oil will do the job. Mounting methods. Well, first of all, we have mechanical methods where we use C-spanners, we use mounting tools to fit bearings. We also have thermal mounting methods where we use induction heaters, we use hot plates to warm objects up, to warm bearings up, to mount them to shafts, and we use hydraulic means such as hydraulic nuts and presses to mount bearings to tapered sleeves and tapered shafts. First of all, if we look at cold mounting, we can look at we can see example A there. We have a bearing that's being pressed onto the shaft, and using this tool here with this mallet, the tool actually applies the mounting force to both parts of the bearing, so it reduces the risk of damaging the bearing when we fit it. In letter B, we have C-spanners, again, where we have lock nuts on bearings. Good practice, use a C-spanner. If we use drifts and screwdrivers and things like that, we do run the risk of damaging components. A nice good C-spanner will eliminate that problem. And then in C, we have a heavier version of the C-spanner. We have an impact spanner. Again, for medium to large size bearings, we can fit them using this impact spanner, which we actually strike with a hammer to tighten lock nuts up. And then letter D, we can see there that the bearing's actually being fitted by a strong back mechanism with a spanner. Again, another method of mounting a bearing without heating it up and basically pressing it on the shaft, but very importantly, not doing the bearing any damage. Hydraulic methods. The SKF drive-up method is a system that we've developed for mounting bearings on tapered sleeves and tapered shafts. Basically, it's a process of using a hydraulic pump with a calibrated digital gauge, and that's connected to a piston that threads onto the shaft and presses against the bearing. We have drive-up data for every size of bearing that we manufacture. So in this particular case here, this is a spherical roller bearing being fitted. We would pump this bearing up to its start pressure on the gauge on the pump, and then we would physically measure the drive-up distance of the bearing up the taper shaft. And that's what we call the SKF drive-up method of mounting bearings using hydraulic nuts. If we have to heat bearings up, obviously things like hot plates and bearing heaters, induction heaters, we manufacture a range of different heating devices. Again, it's dependent upon the size of the bearing that you want to make. We make heaters for large bearings, we make heaters for small bearings. But again, this is a process of heating the bearing up to generally around 110 degrees. This will expand the inner ring of the bearing enough to expand the bore size larger than the shaft that the bearing is being fitted to. You look at the bottom left-hand corner, that's another type of induction heater. They're more like a hot plate principle, the two on the left, but they basically heat the bearing through, but you have to obviously monitor the temperature of the bearing as it's being heated. The items in the middle on the bottom there, they're aluminium rings that we use for fitting cylindrical roller bearing inner rings and also for taking them off as well. These rings would be heated to 200 degrees C. You can see they are split. They are placed over the inner ring of a cylindrical roller bearing, and the heat transfers from the ring to the bearing ring, and it expands it. So whether you're taking it off or putting it on, this device allows you to do that. And then the two heaters on the right, they are in fact induction heaters. You've got the expandable, again, cylindrical roller bearing inner ring down the bottom, and then we have the conventional induction heater at the top. All means of heating bearings to mount them. And here we have some handy posters, which I'm sure Ringo can give you some details of, should you need any. It's sort of a bit of covers a lot of what I've talked about this morning. And as Ringo said, you've got your facility to ask questions on the Teams toolbar there. But there's also, you can go on our website, onto SKF Training Solutions. You can click on that. If you've got other questions, you can contact me on that email, send me a mail through, and we'll follow it up for you if you like. Thank you, Ringo.
Okay, Mark, thank you very much for this presentation. I think it was absolutely clear what you have told us. So to come back to the slide you are still seeing, this is a series of 5 posters with the dimensions 70 times 100 centimeters. They are available for you within a couple of weeks' time. They are printed at this moment. If you want a set of these, please let us know, and you can ask Mark, or you can ask me directly. So just for your needs, this presentation has been recorded, and it will be sent to you afterwards. That will be during this day or at the latest tomorrow. You will also receive a slide deck of this presentation with all the email addresses that Mark just showed us. Okay, so far the practical things. I have seen that there is a question in the chat box, Mark.
Yep.
As you know, after selecting the fits according to SKF tables, it is sometimes needed to check the residual clearance of bearings on cylindrical shafts to be sure the clearance will be enough in operation. I mean the clearance after mounting and in operation. Would you share the formulas for this purpose with us?
Yeah, obviously, cylindrical bore bearings, when they're mounted, we generally don't measure the clearance when we fit them, and we generally don't measure the clearance when they're fitted. But saying that, we can work out what the fitted clearance of a bearing with a parallel bore should be if the customer has got a specific size of bearing, because we know how much the bearing expands we know what the start clearance is in the bearing, and we know how much it should reduce by, so we can work that out. If this person wants to send me some more details on that, like the bearing part number, we can obviously look at that for him.
Okay, thank you, Mark. So the person who has asked these questions, please refer to Mark directly or to your local contact person. There is another question in the chat box. Are these posters free of cost? Yes, that's quite an important question, of course. Yes, they will be free of charge for the UK, of course. When you're outside the UK, I will contact the local contact person at the SKF in your country to see how we can manage that. But normally, yes, the posters are free of charge. And all those posters, as you still see on the screen, they go through the topics that Mark has presented this morning. They give you an overview of all the different bearing types, the different mounting and dismounting methods and tools, the selection of the right fits, the bearing designations, and an overview of all the available mounting and dismounting tools in the different methods that Mark presented. Okay, are there any more questions? It's your chance to ask them now directly.
As I said, if anyone else has any questions they think of at a later date, please contact me on that email address. I'm more than happy to answer them for you.
Yeah, of course. And this PDF that I will send you is interactive, so you just have to open up the PDF and click on Mark's email address, and you will be directly linked to Mark. So that's good.
Was there someone trying to speak then?
Yes, please. Just where can I get these wall charts, please?
Just send an email to me, and I will include my email address as well on the slide deck when it's sent to you. So you will receive it automatically after the webinar this afternoon or at the latest tomorrow. And there you will find also my contact details. And just send me an email, and I will take care that you will receive a free set of posters.
Hi, Mark.
Thank you.
Hello.
Hello.
Yeah, this is Prem from India. Okay. So I
Yes.
just want to know brief about one point: the heating temperature of the bearing during induction heater.
Yeah.
So the temperature, what should be the good temperature of the bearing during the fixing of the bearing by induction heater?
Yep.
Normally, we used to keep the temperature in between 110 degrees centigrade to 120 degrees centigrade. Is it okay?
Yeah, I mean, 120 is probably the maximum you want to go to, because you got to consider bearings that may have seals, bearings that may have polyimide cages. Some ball bearings are heat stabilized to 150 degrees. So once you start approaching those sorts of temperatures, you do run the risk of damaging the bearing. But if you stick to 110, 120 degrees, you should be okay.
Okay. And one more question, it not is related to this webinar, that are you just looking for the catalog where I can find the bearing number of balls, bearing ball diameter, and the pitch angle and the contact angle of the bearing. These data are required for vibration analysis part.
Okay.
There are, that's not available in any catalog, but that will be available in some of our vibration analysis databases. Can you send a request for that, please, to either Ringo or myself?
Okay.
And we'll look at that for you.
Yeah,
Thank you.
just please do, and then we will forward it to the right person if we cannot answer it ourselves. But we will definitely come back to you with an advice or a reply from one of our engineers.
Thank you, Mark, and thank you to Escape team for arranging such nice training. Thank you.
No problem. Thank you, Mayor, very much for joining.
Thank you.
Okay, so if there are no more questions from your side, Mark and I would really like to thank you for joining this webinar. We hope you enjoyed it. We hope we gave you some information that can help you in your day-to-day activities working with bearings. Don't hesitate to let us know if you have any more questions, whether it's about this topic or any other topic. Don't hesitate to call. We have a big team of people who can help you from the maintenance until the engineering, from the service engineer. So please don't hesitate to let us know. Thank you again for joining, and hopefully we'll meet next time.
Thank you.
Okay, thank you very much, and see you next time. Bye bye.